Welcome again to our journey into number theory. These are the tutorial exercises for chapter 3, section 3, and we're just going to have a look at the ones from 11 through to 14. So these are on looking at these sums over divisor problems and Mobius inversion formula. So the first one says that if Fn is multiplicative, then the sum over the divisors of mu d times fd is just the product of over the prime factors of n of 1 minus fd. And then from that we're meant to deduce this formula and also this formula here. So here are the worked solutions for this. You might have a go at these again before you look at the solutions. They're fairly straightforward, these ones. So we have f is multiplicative, and I'll just put capital F of n to be this sum over the divisors we're looking at. Now, since this is a sum over the divisors, we know that these are both multiplicative, so this capital F is multiplicative. So I'm just going to evaluate it at any number n with prime factorization thus. And so I can split this up into bits. Now, f of p1 to the alpha 1, well, that's going to give me a 1 is one of the factors of this number. Mu of 1 is 1, gives me this one, and mu of p1 is minus 1. Now, of course, f of 1 is 1 because f is multiplicative, so that's why we just get a 1 here. And then we're going to get a minus from the Mobius function times f of p1. And we'll get 0 from there on. And then the same thing happens for each of the prime factors, so we get this product, which is the product of all the prime divisors of n of 1 minus f of p. To get the second result, I'm just going to put f of d to be 1 over d, or f of n is 1 over n, if you will, into that formula, and then I simply get mu of d n over d, which is what I'm looking for. So I get n times, I can take this n out the front, and so we have the formula above. I get n times the product over the prime divisors of n of 1 minus 1 over p, so that's it. For part C, we simply, again, we're looking at mu d times 5d, so I'm just putting f of n as 5n. So when I plug that into the formula above, I just get the product over the prime divisors of n1 minus 5p, and 5p is p minus 1, which when you simplify gives me this result here. Now this is rather interesting because, of course, if n is even, then 2 will be one of the prime factors, and so this will be 0. So this sum then is 0 if n is an even number, which is a rather interesting fact. If n is even, then the sum over the divisors of n of mu d times 5d is 0. Question 12 is a little bit more, slightly more difficult. So we've got a prime p bigger than 2. We define psi of d to be the number of elements in zp star with exact order d. And we want to show that if d divides p minus 1, then the sum over the divisors of d of phi gives me back to d again. And we can deduce then that this phi of d is equal to psi of d. And hence, out of this, we can deduce that there are phi p minus 1 primitive roots modulo p, which was a result we saw several chapters ago. Anyway, here's a quick solution. It uses Mobius inversion, which is why it's here. So psi of d, remember, the number of elements in zp star of order d. Now, we had a theorem before, very early in the chapter 1, that if d divides p minus 1, then next to the d, congruent to 1 mod p, has exactly d solutions mod p. And if we've got a divisor of d, then next to the, which is c, then x to the c minus 1, x to the c congruent to 1 mod p gives me x to the d is congruent to 1 mod p, obviously. So that means the number, so each one of these divisors is going to contribute to the number of solutions of x to the d congruent to 1 mod p. So if we take the sum of all of these psi of c's over the divisors of d, we're going to get back to d again. Now by Mobius inversion we can now invert this, and we can write psi of d then is going to be this sum by just using Mobius inversion formula. And once again, this result here is just phi of d. That was from theorem 3.6. We did that before. So that's the result. And finally then, we simply put d to be p minus 1 in, and the result follows, because if d is p minus 1, then psi of d, psi of p minus 1 is giving me all the elements of order p minus 1, that is all the primitive roots, or the number of primitive roots, and that's going to equal then psi of phi of p minus 1. Question 13 is a fairly easy one. It says, we've already seen that if you've got a sum over divisors of a multiplicative function, then the result is multiplicative. And now we're doing the reverse. We're saying that if the sum over the divisors of an arithmetic function is multiplicative, then the f we started with must also be multiplicative. And again, we can get that out very quickly by using Mobius inversion formula. In fact, it's a very short proof, so we put capital F of n then as the sum over the divisors of fd. Using Mobius inversion, we can write this down. Now this is just mu star f, and each of these are multiplicative, and so we know we have a theorem that says therefore their Dirichlet product is multiplicative, so little f is multiplicative. Finally, question 14. Now this is a slightly more tricky one. It is give a direct proof of this sum here, and the hint here is to consider sets of this form. So we look at the sets n sub d, which consist, so for each divisor of, we're looking at d being a divisor of n, so we're looking at the set of k, and I suppose I should really say here k is less than d. So, sorry, k is less than n, I should say. K is less than n, where the GCD of k and n is equal to n over d. And we're going to show that the size of n sub d is actually phi of d. And we'll then show that if you take a union of all of these sets, then you simply end up with the numbers from 0 up to n minus 1, and there are n numbers in that set, and that's going to give us our formula here. So you might like to try that one yourself, but it's slightly more tricky. So here was the hint. We start off with, we get capital N be the numbers from 0 up to n minus 1. If we've got d as a factor of n, then we're going to set this, make this set n sub d to be all the k's where the GCD of k and n is equal to n over d, and k is less than n. Now you've got to get your head around this definition, so you might like to try an example. For example, I worked out down here, if you take n to be 6, and then you look at the divisors 1, 2, 3 and 6, and you calculate these n's, then n sub 1 turns out to be just a set containing 0, n sub 2 is a set containing 3, n sub 3 is a set containing 2 and 4, and n sub 6 is the set containing 1 and 5. And you can see just from this example that the sets are all disjoint, and if you take their union, you get the numbers 0 up to 5, and there are 6 of those. Now, again, a little bit of thought, again, looking at an example helps, and that is that this n sub d then consists of all numbers of the form e times n over d. This is for each divisor d of n, where the GCD of d and d is equal to 1. That immediately gives me that the size of n sub d is just then phi of d. So n sub d does not equal n sub d dash. You need to give a little bit of a proof of that. If d is not equal to d dash, in other words, the sets are disjoint. So thus, as D varies across the divisors of n, these disjoint sets ND have a union which just consists of this set n, and there are n, which going from 0 up to n minus 1, and there are n elements in here. So when we take a sum of phi d over d divides n, we're just going to end up with the number of elements in n, which is little n. That's a slightly harder problem, and that's a little proof of that one.